Okay, for this problem, we're looking at a Poisson distribution in space. So bullets are fired at a target. So there's a target, and you fire bullets at it. So bang, 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 bang. And the position of the bullets are the positions of the bullets are Poisson distributed with parameter 2 hits per square foot. Find the expected distance of the closest bullet to the bullseye. Okay, now the hint is to use the tail sum formula, that the expected value of d is equal to the integral from 0 to infinity, d greater than or equal to r, and I integrate this with respect to r. This formula applies because d is a non-negative random variable. If d could permit negative values, then this formula does not work. So let's use this formula. The probability that d is greater than or equal to r. Okay, now how does that happen? How is it possible that d is greater than or equal to r? Well, d is greater than or equal to r if there are no hits inside of this small circle. The closest hit mark is here. So if the closest mark is here, then inside of this smaller circle with radius r, there must be no hits. So that's the probability of no impacts in a circle with area pi r squared. So that's the probability that I have no impacts inside of this circle. Now the area of the circle is pi r squared. There's 2 hits per square foot, and so this will be equal to e to the minus 2 pi r squared times 2 pi r squared to the 0 over 0 factorial. Because the number of hits inside of the circle will have Poisson distribution with parameter 2 pi r squared, 2 times the area of the circle. And so that's equal to e to the minus 2 pi r squared. So that's the probability that d is greater than or equal to r. And therefore, by the tail sum formula that we see here, the expected value of the distance is equal to the integral from 0 to infinity, e to the minus 2 pi r squared dr. Okay, so how are we going to evaluate this integral? To evaluate this integral, we'll recall something. So I'm going to do some scratch work over here on this side. So recall that the integral from 0 to infinity of 1 over sigma square root of 2 pi e to the minus x squared over 2 sigma squared dx is equal to 1/2. Now why do I know this? Well, what we see here, that's the PDF of a normal distribution with parameters 0 and sigma. And we know full well if the mean of a normal distribution is 0, then the area to the right of the mean is equal to 1/2. Half the area lies to the left of the mean, and half the area lies to the right. So the picture is I've got a bell curve, here's 0, and half the area must lie to the right. Okay, so in other words, the integral from 0 to infinity of e to the minus x squared over 2 sigma squared dx is equal to, if I bring this over to the right-hand side, I get sigma times square root of 2 pi over 2. Okay, so I've got this integral that comes from the area of under a normal curve. So I just need to make this match this. So what needs to happen is that the 2 pi here must match the 1 over 2 sigma squared over there. So I need the 2 pi that appears over here on the left has to match the 1 over 2 sigma squared on the right. And so solving for sigma squared, bring the sigma squared up, I get sigma squared is equal to 1 over 4 pi. And taking the square root, sigma is equal to 1 over 2 times the square root of pi. Okay, so this integral here is going to be equal to, so coming back over here, that's going to be equal to sigma times the square root of 2 pi over 2, where the sigma that I have here is 1 over 2 over square root of pi. Then I multiply that by the extra square root of 2 pi over 2. And then simplifying, that this is equal to square root of pi's cancel, I end up with square root of 2 over 4 which is about 0.3536 feet. And so that will be the distance of the closest mark to the bullseye. So this one required certainly a fair amount of cleverness. The fact that the closest mark from the origin implies that there are no impacts here. I used the tail sum formula for integration, and then I had to use these properties of e to the minus 2 pi x squared in order to be able to compute this interval.